Hello there, everybody, and welcome back to the Fact and Fiction channel.
Brian, I should say Dr. Brian Koberlein. So if you could tell us a little bit about yourself and, you know, your expertise and what you do, if you don't mind.
Sure. I'm a senior lecturer at Rochester Institute of Technology in New York, and my doctoral dissertation was in the dynamics of black holes in the early universe. It's a PhD in physics. My current research focuses on computational astrophysics. I have a book from Cambridge University Press on that. So that's kind of where my background is.
And we have AL. Everybody knows AL. How you doing, hon?
I'm doing good. Thank you for having me again tonight.
You're very welcome. So I guess we could just go ahead on and dive in here. Potter and Scott Cohn and WSO, they have their theoretical particle physicist who has been writing white paper after white paper, making many, you know, claims about brown dwarfs in the solar system and the sun going dark, and you know, there's a lot of stuff that she's saying. So when they did their hangout on Tuesday, the main focus seemed to be around that 2007 moon transit. And AL has some stuff that he just showed us before we went live. So if you guys could just, AL, if you could show your stuff, and then Dr. Koberlein, you know, if you could, you know, weigh in on all this stuff, that would be great.
Okay.
Okay. The image I've got showing here right now is from Stereo Behind, Core 2, in February 2007, shortly after the Stereo spacecraft departed from the Earth and went around the moon and was now leaving the Earth-Moon system. The moon itself actually entered the field of view, and the Earth was outside that field of view. And I've covered this in a variety of videos that you can see on my channel, including one recent one where I recapped all that information, and we can go over that again later. But one of the things that was said during the hangout on Scott Cohn's channel, where he had this physicist on, one of the main points she seemed to raise in justifying the notion that this was not the moon was the fact that it has this red fringe to it, and it's got some red coloring on it, and if it's the moon, it shouldn't be emitting its own light. And the sun is obviously in the center of the view here, so what is causing it to appear to have illumination on the opposite side? That doesn't seem to make sense. Well, one of the things we have to keep in mind here is that because this is the moon, if you look at the date here, February 20th, the moon was a crescent phase from Earth. And as a thin crescent, it would be experiencing a lot of Earth shine. If you were standing on the surface of the moon facing Earth and looking up at Earth, you would see a mostly full Earth in your sky. And of course, being that the Earth is much larger than the moon, it would look several times larger than the moon does in our sky. It would cast a lot of light on the moon's surface. And that's why, if you look at a very thin crescent moon like we had just a few days ago, you could see the darkened side of the moon quite clearly after sunset. And that's because of Earth shine. And that's because of all the light that is reflecting off the Earth and bouncing off the moon. And actually, that's what we're really seeing in these images shortly after the moon enters the field of view. It was still a crescent phase from Earth. It was still receiving a lot of reflected light from Earth. And you can actually see the side of the moon that is not receiving light from the sun, from the perspective of stereo. This is sort of an unusual situation here, where we have a probe that is leaving the Earth-Moon system and able to effectively look side-on at the Earth-Moon system and is able to see the portion of the moon that is receiving light from Earth due to Earth shine. And so I've rendered a blue line which represents what I would call the Earth shine terminator. This is where the light from Earth shine effectively cuts off, according to my calculations in the spreadsheet here. The moon should be about 90% full with Earth shine from stereo's perspective, showing where the Earth shine cuts off. So that's what the spreadsheet does. That lets you pretty easily render for yourself what the Earth shine should have looked like. Unfortunately, most programs that I have for viewing the solar system, like Celestia, as far as I can tell, doesn't allow for more than one active light source. So after the moon entered the field of view, it passed up and around and made this looping motion, which again matches the spreadsheet calculations I have, as well as images rendered from ORSA. So ORSA stands for Orbit Reconstruction Simulation Analysis, and it's an open source program which allows you to calculate the trajectory of a spacecraft and include the effects of gravity from the planets and the moon. You can see February 25th, the moon is transiting across the sun. So then I overlaid the actual images on top of ORSA's images, and you can see it's a perfect match. The spot seen transiting across the face of the sun is exactly where the moon should have been, according to ORSA. So again, here I'm relaying the images from ORSA back on top of the actual images from the spacecraft, and you can see sort of the pixelated outline of the sun and the pixelated outline of the moon. They match up very well with what was actually seen from the stereo behind spacecraft. So we know it was the moon. It was exactly where the moon should have been. It was exactly the size, the angular size of the moon should have been from stereo's perspective because of how far it was from the Earth and moon at that time. And the illuminated portion of the moon that can be seen early in the images from the Core 2 imager when it entered the coronagraph matches up with what we should expect to see based on Earth shine from reflected light that bounced off the Earth and illuminated the moon, the side of the moon facing Earth. So
Dr. Koberlein, in her papers and in her interviews, she says that this is a brown dwarf. He just proved that it's the moon, and we know it's the moon, but some people do think that she may be right. So can you explain to us what would happen if that was a brown dwarf? How would our solar system be?
You know, if it were a brown dwarf, and just to be clear, as an astrophysicist, when I use the term brown dwarf, I am talking about something that would be about the size of Jupiter and would have a mass somewhere between 13 and 70 Jupiter masses. So it would be larger than any planet that we have in our solar system. The gravitational influences of Jupiter can already be seen on something like Venus or Mercury. We can calculate these because we know the positions of those planets very well. And Jupiter is a large mass, so we can actually calculate those influences. If there were something even more massive than Jupiter closer to the sun, we would easily see the effects of that on the planets. Their orbits would shift slightly in ways that we could easily measure. We don't see any of that. And the thing to keep in mind is that the positions and motions of the planets are open data. Anyone can look at this. You can look for changes if you want to. They're not there. So this is not a brown dwarf in any remote sense of the word.
But would a brown dwarf have solar wind?
Well, it's not a star, so it wouldn't have solar wind in that sense.
Okay.
But it would probably have a magnetic field, and those types of things would interact with the solar wind. I mean, you can't hide something the size of an elephant behind a small car or something, you know,
yes.
Which is basically what you're arguing.
Right. It seems that if this was supposedly Nibiru, part of our solar system and all this stuff, it would have a specific orbit, correct? Could it move around like that?
No, I mean, any object that's going to be part of our solar system is going to have a certain trajectory. The planets that we know of have orbits because they tend to be basically repeating trajectories. So their orbits are pretty stable, and they have been for billions of years. You know, if there was something 13 to 70 times larger than Jupiter in the solar system, you can't hide that. If it formed there spontaneously, then you'd have, you know, a stable orbit and you'd see its effect anyway. But we've done sky surveys. There are sky surveys that have shown that anything as small as the mass of Jupiter doesn't exist beyond the known planets for 1.3 light years away from the sun. So anywhere from the sun to 1.3 light years about, there is no object the size of Jupiter or larger.
If that was indeed a brown dwarf, could we see it? Would it emit light?
Easily. I mean, Jupiter you can pick up on a small dish radio telescope. It gives off radio waves. So you can see it in visible, you can see it in infrared, you can see it in radio waves. Jupiter's easy to find. It's extremely easy to find. It's one of the things that you do with students in amateur astronomy. Like if you want to do amateur radio astronomy, you can actually get the radio waves off of Jupiter. you're talking about the idea of basically a planet that's dozens of times more massive than Jupiter, that's warmer than Jupiter, that probably has stronger magnetic fields than Jupiter, and therefore more electromagnetic waves. You know, brown dwarfs are things that we can find light years away. If we had one in our solar system, we would see it with the naked eye, basically.
I would like to ask, in a recent paper that was published, which was shared by Nibiru Planet X 2016 and also Mr. Potter's channel, they have stated the huge coronal holes being witnessed on the sun at the moment are being caused by a brown dwarf below the sun.
Okay. I guess let's start off with what a coronal hole is. If you look at the sun, for example, you've got its interior, you've got its photosphere, which is kind of like the surface of the sun. That's where the light actually comes from the sun. It's called the photosphere. And then around that is this very tenuous region that's called the corona. It's called the corona because it looked like a crown during the a total solar eclipse, and that's really the only time early on that you could observe it, because you had to block out the light of the sun to see this kind of very faint glow from the corona. If you want to get a very rough analogy, you can kind of think of the photosphere as the surface of the sun, and then the corona as this very tenuous atmosphere of the sun. It's not a perfect analogy, but you know, if you want to get a basic idea of that. So the corona is comprised, it's not very dense or anything, but it does have a lot of charged particles, a lot of protons and electrons that are being pushed away from the sun due to its light and heat. And the sun has a very active magnetic field system. So it's not simply of kind of this static magnetic field or fairly static magnetic field like the Earth. You know, on the Earth, you have the magnetic fields don't change rapidly in some sense, but on the sun they can. And so when you have charged particles in a magnetic field, they tend to follow along the magnetic field. They may spiral a little bit, but they tend to kind of get trapped by the magnetic field and follow what we would call the magnetic field lines. And if you know anything about magnets, magnets have a North Pole and a South Pole. And if you were to trace the magnetic field lines for a magnet, you would see them kind of coming out of the North Pole and then looping back and going into the South Pole. They loop around like that. The same thing happens on the surface of the sun. You will have regions that have kind of a north magnetic region and others that have a south magnetic region. And you get these magnetic loops that stretch out from the sun. And the charged particles get trapped along those loops. And they tend to come out from the sun and then they tend to kind of spiral back in. Well, because the magnetic fields shift, what can happen is that those magnetic fields can realign. And basically when they realign and things, they can create kind of a gap. The magnetic field just kind of goes outward much farther. And that's what forms a coronal hole, because then as soon as you have this kind of magnetic field gap, the particles that want to stream out away from the sun can. And so they don't just loop back to the sun easily. And so they kind of stream outward, and this creates what we call a coronal hole. These are caused by magnetic activity. And we know this because we can measure the strength of the magnetic field at different points. So we know that that's what's causing them. How that would connect to a brown dwarf is really kind of fuzzy. I mean, I assume that the brown dwarf is somehow supposed to be interacting with the sun to create a different magnetic field, but again, there's no evidence of this at all. There's no evidence of any brown dwarf, and no evidence that the magnetic fields are being driven other than the interior activity of the sun.
A viewer called, I think, is it Jose Carlos Yu, stated that you cannot compare Jupiter's light emissions with a brown dwarf, and he put in capital letters infrared. Do you want to sort of touch on that?
Sure. You to say you can't compare the light emission with the brown dwarf's infrared is true, but you can compare Jupiter's infrared to a brown dwarf's infrared, and you can compare Jupiter's visual to a brown dwarf's visual. The thing about large planets like Jupiter is kind of an interesting thing. Jupiter is so massive that it actually gives off more heat than it receives from the sun. It glows in the infrared because its intense gravity is squeezing the material that it's made of. And so it actually has a thermal temperature to it. You can actually see Jupiter in the infrared. You can see it glow in the infrared because you know what its temperature is. A brown dwarf, and again, I'm being very clear about what we mean by a brown dwarf, is something that has a mass between about 13 to about 70 or 75 Jupiter masses. So because of the physics of things, they're about the same size as Jupiter, but they're more dense and they're hotter. The larger ones would be, say, their surface temperature would be, you know, several hundred Kelvin to possibly a couple thousand Kelvin. That's actually glowing to the point where you can almost see them in the visible light, and you would see some visible light coming from them. So the hot brown dwarfs you could see in the visible, but more importantly, they are extremely visible in the infrared. So they would be very bright in the infrared. When you talk about the then when you talk about the visible light of infrared, the visible light that we see from Jupiter is not what Jupiter is producing itself. It's reflected light from Jupiter's surface. So the sunlight in the visible spectrum strikes the surface of Jupiter, and it's reflected by the clouds to see the object that we see. So when we see images of Jupiter, as you see in photos and stuff, that's reflected light, usually. Anything the size of Jupiter would have a dense gaseous surface, and light would reflect off of it in much the same way. So it would look very much like Jupiter in that appearance. And if you had one in the inner solar system, you would see it. It would be huge. We would have known it since antiquity. It's not, again, it's not something that you could hide.
Robert Lockwood asks in comments, please, 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 Mr. Koberlein, please explain the particle beam presented in the LASCO images that Scott Cohn has never seen before. It was awesome.
Okay, I'm not familiar with the specific image he's talking about from LASCO.
Okay, there's one here I want to discuss. She's sun halos and solar eclipses. One red flag for me is she thanks Jeff P. She thanks him for helping her understand what sun halos are. And she says that I agree with him. They are caused by planets eclipsing the sun. She says sun halos are bright circular outlines around a central light source, which light sometimes emanating from the edges of the circular outline. She says that it's a solar simulator up there. One of my questions I want to ask is about this. They're claiming that there's a solar simulator. It eclipses the sun, between the sun and the earth, and it looks hexagonal, I think, or whatever. I'm sure you know what I'm saying with the sun halo, Brian?
I'm familiar with the sun halo, yes.
Okay, now they're saying that that is a planet eclipsing
the halo
the sun.
itself is a planet?
Yes, that's what this paper says.
So there's this ring planet that's in front of the sun.
Now, see, what I'm trying to figure out is if it's a planet, why do we only see the outside of it? And she says we're seeing the atmosphere of the planet.
Of the planet. So the planet itself is transparent, but the atmosphere isn't.
Wouldn't we see? We would see the planet, correct? Like I'm really kind of.
Yeah, I mean, sun halos are an effect that's caused by typically ice crystals in our atmosphere. So on a cold winter day when there's ice crystals in the upper atmosphere, those reflect light and refract light to a different direction. So when the sunlight comes out into the atmosphere, it's reflected and bent so that we see that reflection. It's similar to an effect that you would see with a rainbow. When you see a rainbow, it's light interacting with water droplets, and the light is reflected and refracted so that you get this rainbow of colors coming back towards you. This is why, for example, when you look at rainbows, rainbows are typically seen in an area where it's either raining or foggy, where there's water droplets in the atmosphere, and the sun is behind you. Because what has to happen to see a rainbow is the light has to be reflected back towards you through the water. And that's what causes that prism effect to get the rainbow colors. The ice halos are caused around the sun because they're reflected only slightly. So you don't have to have the sun behind you. You have the sun in front of you. They're reflected slightly, so you see this kind of ringed glow, sometimes with a kind of faint rainbow effect that is caused by, you know, ice crystals in our atmosphere. That's been, again, known for a couple hundred years.
So I just wanted to address this real quick because it's really sort of an obscure thing that they're citing, but they do claim that somehow someone has put up a sun simulator and that humans actually have a patent on this technology, and you can look up sun simulator patents. And so they're trying to suggest that someone is trying to literally simulate the sun in the sky to hide whatever, Nibiru, what have you. And what they're actually citing are patents like this one, which describe technology to simulate the sun in a laboratory environment. And so this is one of these patents, illumination system including a virtual light source. And what this patent is actually for is technology to simulate the sun in a vacuum chamber when testing spacecraft and spacecraft components. So here's an example image of the Apollo Command Module, Apollo Command and Service Module, being illuminated by a sun simulator, where they're testing the thermal properties of the spacecraft and its ability to deal with infrared and light emissions from the sun, and the ability to regulate its own temperature. It has nothing to do with actually trying to replace the sun in the sky. It's about simulating the sun in a laboratory environment in a vacuum chamber on Earth. This is actually a gigantic vacuum chamber, so when they close up this door, they can evacuate the air and actually test the spacecraft in a vacuum with proper illumination to simulate the sun. And so that's what that's really about. It has nothing to do with trying to replace the sun in the sky. But I just wanted to address that real quick because it's really obscure and ridiculous, but there it is. So
to be able to put something that is supposedly supposed to hide these planets from us, so that means it is in front of the sun, and then the planets are behind it. So we're on Earth, our planet rotates. So how could that even be possible to put it in such an orbit that it would hide it from us like that? Is that even possible?
Not with today's technology, no.
I just, you know what I mean? That's something I was thinking about earlier. Like how would that even work?
Well, I mean, part of the counter to that is if we were doing that, let's assume that we were actually, you know, I'm part of this Illuminati cabal or something that's hiding these things. If that were the case, why would we put so much astronomical data online open to the public? Mm-hmm. I mean, that to me right. seems deeply counterintuitive. If the astronomical community were trying to cover up things, they wouldn't be putting things out there for the public, which is part of the right. mandate and part of the continuing and growing trend in astronomy. Astronomy relies very heavily on motivated amateurs. We get a lot of stuff done yes. because of devoted amateurs. And there's this long history in astronomy of making data public. And in fact, many of the things in which we get from space telescopes and things like SDO, the data is publicly available. You can go to the SDO website and you can get hours and hours and hours of public video. And the argument is that if you can't, if we're trying to cover up something, then you can't then use that data to argue that we're covering something up. It makes yes. no sense. You know, if you want to keep something secret, you don't then make fake data to try to release to the general public that so few people will use. You know, I mean, it's not like you're going to have this detailed data that everyone's going to look at. There's a few devoted amateurs that look at this stuff. The cost effectiveness of this doesn't even make any sense. Well, and it would be easier to say, look, you have to be a registered scientist in order to access the data. We could do that. You know, there are areas in which we do limit data. So medical data, for example, is extremely limited in order to protect the identity of people who are involved in the medical research, you know, the test subjects. So there are limitations that can easily be placed on this. We don't do that in astronomy.
You could tell from what AL does. He you know what I mean? He makes these videos, and, you know, the simulations that he's doing, he's using all this software that anybody can use, right, AL?
Anybody can use it.
Right. Absolutely. And, you know, I actually, not to, you know, I discovered a comet last year, P2016J3, using images from the stereo ahead spacecraft, using publicly available images from the heliospheric imager. And, you know, there's so much data that gets produced by these spacecraft that even the professional scientists don't have time to personally curate every single image and look for, you know, unidentified objects flying through them. They don't have time for that. And so I was able to find a comet that no one else had noticed before, because it was just a faint little comet that wasn't visible from Earth, but stereo ahead, being on the other side of the sun, was able to see it. And so I discovered it, and then a couple months later, an amateur astronomer in Denver got a picture of it just barely, because it was not in a good position to be viewed from Earth, even later on. Just the way the orbital timing worked out was not good for Earth. But he did get a picture of it just barely above the horizon, and it's just this faint little smudge. But you can see it on aerith.net, and, you know, no one else would have, you know, I guess what I'm trying to say is, if it were all fake, then how did I manage to find a comet using images from stereo months before it was observable at all from Earth, and then only barely, and then an amateur later on confirmed that finding from Denver, Colorado? Like that's you know, that's crazy. So obviously it's real, and obviously there are things that even NASA doesn't know are in the data, which is why amateurs are finding sun grazing comets in these images all the time. They don't, you know, they don't hire professional scientists to just sit there trying to find sun grazing comets. There's not much scientific need to do that, especially when you have amateurs who will willingly do it for free. So yeah, this data is shared with the amateur community, and dedicated amateurs do make discoveries with that data.
Right. I'll give you another example. There's a search on for Planet 9. So this idea that there could be a super Earth-sized planet well beyond Neptune. So nothing like Nibiru or anything. But there's these orbits of these trans-Newtonian objects that are kind of like icy Pluto-like objects. Their orbits don't seem random enough. They seem as if they're being pulled gravitationally by something much farther out. And so there's some speculation that there could be a 9th large planet in our solar system. Well, there's been a search on to do this. If it's reasonably close, given its size, that planet should have been seen in the data of the sky surveys that we already have. The problem is it takes a lot of time to identify it. So Zooniverse put up a project to look for this Planet 9, and 60,000 people in 3 days covered enough data and analyzed enough objects to do what it would be the equivalent of 4 years of scientific research.
Wow.
They analyzed over 5 million objects, and they found 4 candidate objects that probably aren't going to be Planet 9, but could be a dwarf planet or an asteroid or something like that. We use amateurs all the time because they get stuff done.
Okay, I want to talk about this paper right here. Okay, she talks about the sun's going dark. Now, when I looked over this paper, I noticed the years that she put here. She has 2017, obviously, and then 2016 and 2012. Now, she's comparing these years to 2017. Now, last year in 2016, we're in solar minimum right now. So the sun is not very active. It's not going to look bright. It looks like this. This is what it looks like. In 2012, it was in a max. All the dates on here that she puts with these images, she's comparing our solar minimum to solar max dates.
She's doing something fundamentally wrong here, and I do want to address that. For one thing, she's not starting off with the raw FITS files. She's using the pre-processed, PNG files, whatever they are, the low bit depth versions that are on the SDO website, which are not intended for photometric measurements to be made off of them. You need to go back to the raw high bit data, and I did that in a little comparison image here that I'll show in a second. So let me just rejoin the Hangout, and I'll be right back.
Yeah, I mean, I would add, related to that, these images, not only are they not the raw data, so you have to be very careful. You don't want to use anything but the raw data for anything that's scientific. What's not clear is what wavelength she's looking at. So ultraviolet, okay, fine. But these images are often used to pull out certain features. They are not the same thing as the overall brightness, what we would call the luminosity of the sun. How much energy is it actually putting out? These images are not what they're used for. They're filtered, and they have narrow wavelengths to come out with very distinct features. You can measure the overall brightness of the sun, but it's pretty stable, even in solar minimum and solar maximum. The solar minimum and solar maximum is kind of a confusing term, because it was originally defined in terms of how many sunspots we would see. So early astronomy, so back in the 1700s and into the 1800s, we couldn't see all of these features because we only had visible light, and we were looking at it with telescopes from the Earth. So the only way we would see changes in activity is whether or not we saw sunspots. So that's where the idea of solar maximum and solar minimum comes from. Now it's somewhat useful, because when there are more sunspots, there's more surface activity, you get more solar flares, you get things like that. So it is a more active surface. But that is not the same thing as the overall brightness of the sun.
So the sun isn't to go dark for a very long time. So can you kind of explain the process of that? They're saying that the brown dwarf is draining the sun's energy.
I guess the amount of energy that the sun puts out is caused by solar fusion in its interior. There's heat in the interior that is released in terms of heat and light at the surface. That's a very long process, and in fact, over millions of years, the sun actually gets slightly hotter over time. So it's hotter now than it was a billion years ago. And that means that it gives off more light as it heats up over time, because as stars age, they get hotter and they get brighter. That's the nature of how they evolve. The overall temperature, the overall brightness of the sun isn't significantly changing. You know, you can look at sunspot activity, you can look at solar flare activity, but the amount of kind of average energy per year is not changing in that way.
Paul Rogers asks, Dr. Koberlein, Scott Cohn released another video today on space weather. In the video, he stated that Nibiru, which is obviously classed as the brown dwarf, or the planetary system has stripped away our magnetosphere. Is this possible? And obviously, you know, obviously give us your thoughts on that.
No, and in fact, we have satellites in place that are measuring the magnetic sphere of the Earth. Again, there's no evidence of that. The magnetosphere of the Earth is not being stripped away in any way. It's still there and functioning just fine.
Brilliant. Thank you very much. Another question is from Susie. Brian Cox says they have a hypothesis that a planet 9 is in the solar system. What is the hypothesis, and where is it in the outer solar system? So where, you know, if there was a planet 9, which we obviously NASA and the space agencies do believe that there is one, where could we possibly find it?
So let's talk about what a hypothesis is. The basic idea of a hypothesis is it's an idea that might fit the set of data that we currently have, but hasn't been verified. So you might think of it as a tentative model. And so Brian Cox is right in the sense that there is a hypothesis that there might be another large planet in our solar system. It comes from, like I said, indirect evidence from these kind of small Pluto-like objects beyond the orbit of Neptune. So Pluto is usually farther than the orbit of Neptune, and it's part of the Kuiper belt. It's a Kuiper belt object. There are other ones. Eris is another small icy body. The other dwarf planets, Makemake and Haumea, are things that are similar in size or maybe a little bit smaller, but are these icy worlds that are out on the outer edge of our solar system. If you look at the most distant ones, they seem to be clustered slightly. If they were the only thing out there, they would probably be randomly distributed. Their orbits would kind of be in all different directions. They're not. Now, it could just be an unusual fluke that they happen to be clustered together. But if you do these computer models with gravitational interactions, that clustering could be explained by the presence of another planet far beyond the orbit of Neptune. So the idea is that if you look at the simulations, the most probable kind of idea would be this object in an elliptical orbit far beyond Neptune that might be 10 times more massive than the Earth. So that's the idea. There have been efforts to find this. So this would be a big discovery. It would be that there, on the outer solar system, there is another planet. So we would have 9 planets in the solar system. This is not the same thing as Nibiru. The idea of Nibiru is this object or star that's coming towards us to the inner solar system. This is not related to that in any way.
Jose Carlos asks, on the northern hemisphere, the waxing moon has always been seen as a D form, and the waning has always been seen in the C form. He's talking about the crescents. Mm-hmm. Also at 18 degrees north, it has always been like this. However, since these recent years on some northern latitude nations, and at also latitude 18 degrees north Caribbean, we see these lunar faces 90 degrees inverted and sometimes in the 80s. This is not normal for northern hemisphere. Could you please explain why these change?
I would suspect that he's getting something confused. There is an interesting thing about the moon, and if you look at the phases, and it's one of the weird things, like the first time you go to the opposite hemisphere. So I spent most of my life in the northern hemisphere. And you, even if you're not really aware of it, you know how the moon is supposed to look, because, you know, like he says, it's a D waning hemisphere. When you go to South America, for example, so I went to Chile, and you would see the moon, and you know it's a moon, but it looks odd in some way, and it takes you a while to wrap your head around the fact that you're actually looking at it upside down. So instead of a D form in the southern hemisphere, it's a C form. And you can see images of this, but it's the reason, it's one of the things you can say, this is why the Earth is round. Because when you're on the northern hemisphere, you're kind of looking, you know, the moon kind of follows the equator of the Earth within a few degrees. So when you're in the northern hemisphere, you're looking above the moon a little bit. So you get, you know, the reflection of light from the sun in a specific way. When you're on the southern hemisphere, you're basically standing head over heels looking at the moon. So you're upside down because of the curvature of the Earth. And so you see the moon appearing backwards. And it's this weird thing because it's up there and you don't really necessarily, unless you really think about it, it looks odd. And it takes you a while to kind of figure out that.
I think one of the things you might have been referring to, I don't know if you guys can see my picture or not, but the fact that the moon, when it's rising and setting, especially from sort of tropical or equatorial locations, will frequently look like it's laying on its side. And you'll see this in entire constellations too. When Orion rises from Florida, he looks like he's laying on his side. And the same can be said of the moon. So here's an old photo of the moon, just as proof that this is not something new. Here's an Apollo Saturn V sitting on the launch pad in 1971. And the crescent moon looks like it's a smiling face, or Cheshire moon, or sometimes referred to, I think, as dry moon versus wet moon. But that's quite normal. And you know, as astronomers, we refer to this as field rotation, where objects appear to rotate over the course of rising to setting. And it's one of the reasons why for doing long exposure deep space photography, you have to have a polar aligned telescope, or you have to have some way of canceling field rotation, because otherwise the entire field of view will appear to spin, even if you're tracking the center of the view perfectly. So you see the same thing in the moon when looking at it from a non-polar aligned perspective, like the way most people look at the sky, up and down and left and right. They look at it relative to the horizon, and that's what we see here. The horizon's level, and the moon is this crescent, smiling crescent phase. And so I created a spreadsheet a few years ago to calculate this and show that, you know, it's normal. And if you account for field rotation, you see that it should have been rotated almost 90 degrees relative to vertical, relative to the horizon. So that is quite normal. And there are old photos of this going back many decades, of course, where you can see this phenomenon. And that's one of the reasons for the term Cheshire Moon. So
there's a question here. It says, is there a correlation between coronal holes and earthquakes? The question comes from the Matrix Exit.
No. Earthquakes are by tectonic activity, and coronal holes are not. They can be related to things like northern lights, but not earthquakes.
When people can't explain why our solar system isn't going haywire because of planets and stuff, they're all seeming to drift towards the electric universe. If you could kind of just, could you talk about that with us for a little bit?
Sure. So in a very broad sense, the ideas of the electric universe are that electromagnetism and plasma plays a primary role in astrophysics. And then you couple that with mainstream astronomy, mainstream astrophysics somehow got it wrong. So in its broadest sense, it's focused on electricity and plasma, and a focus on that modern astronomy, as it's typically defined, is wrong. Beyond that, you start getting into all these little theories and all these variations. One of the big ones is that solar fusion doesn't occur in the sun's core. So stars do not glow because of heat produced by solar fusion. Stars glow through some type of electromagnetic activity. There may be fusion towards the surface of the sun, but not in its core. That's a common thing. It's called the electric sun idea. You know, other things that come up that are related to this is that the redshifts that we see of distant galaxies are not due to the expansion of the universe. They're not due to galactic motion. They're a different electromagnetic effect. So perhaps the universe isn't as big as we think it is. Other things would be that there have been massive electric discharges on planets to create, like on Mars, the big canyon that you see on the surface of Mars. Some will say that's due to a huge electric discharge that kind of ripped out that valley area. There's all sorts of things like this. It's this very strange and convoluted kind of cluster of models that all kind of fall under to the electric universe idea.
But there's no math behind it, right?
Yeah, there's again very broadly, because you can always find some exceptions. Yeah, there's kind of an aversion to math. One of the claims that kind of comes out is that as astronomers, we've locked on to computer models and mathematics, and we haven't dealt with common sense. And the electric universe supporters really kind of propose their idea as common sense. I might not be an astronomer, but I understand plasma, and let me tell you, son, how it actually works. You know, there's this kind of average guy type of approach to things. I think part of the reason why it's so popular is because it does kind of portray itself as being straight shooters. You know, look, I'm not going to be lied to. I'm not going to lie to you. If this looks like a duck, it's got to be a duck. And that's very compelling in a certain way, because as scientists, we tend to say, well, it appears that, or there's a lot of evidence to support this. And we don't make these kind of grand, simple statements very much. And that's because we're kind of cautious of letting the data lead too far. But because it's so broad and because it's so convoluted, you can basically put the pieces together however you want. They're kind of like Legos, and you can build anything you want, from a Millennium Falcon to, you know, a little cabin. I think one of the things you see a lot is this kind of misconception in how science is actually done, and a misconception of what the goals of science actually are. There's a lot of focus on the electric universe about, you know, science getting it wrong, and we need to have a new and simpler perspective, that we've made things too complicated, and we really need to just get down to basics. And the thing about science, particularly something like astronomy or astrophysics, we love simple theories. We love what we would call elegant and beautiful theories. However, we're driven by data, and so oftentimes the universe doesn't always cooperate.
It's very complicated.
It's very complicated. And this is part of the thing, is that one of the big gripes from mainstream astronomy about something like the electric universe is that it doesn't make clear, broad, and accurate predictions. It doesn't describe things accurately, and it doesn't provide us with any tools. So you can argue that general relativity is wrong, you know, and you can make the counter argument, well, do better. But even if you argue that general relativity is wrong, the code that we use for GPS takes into account general relativity. We have that written into the code, and it works. GPS works. Anyone with a cell phone can test this. You know, one of the things that I'll tell my students is, if you use your cell phone to find where the nearest coffee shop is, you're using a $200 device to connect through $3 billion worth of satellite technology in order to test the theory of general relativity. And you do this all the time. The simple fact is that the theories that we have work predictably and accurately. And if you want to say that they're wrong, if you argue that, well, they're wrong, or they're somehow incomplete, another argument that you'll hear is, well, you can't predict everything, so you know nothing. Like, well, you know, I don't understand members of my family all the time, but I do understand them pretty well. So I can function with them. You know, I don't have to know everything about somebody to understand them. I don't have to know everything about a theory to understand it. We can build rockets. We can send things to Mars. We can send a probe past Pluto. Newton's theory of gravity may be wrong, but it's good enough to send probes to Pluto. The whole thing about the electric universe is it doesn't provide that. The electric universe can't do better in terms of its accuracy, in terms of its power. What it really comes down to for a lot of people, I think, is it feels better. You know, ask most physicists if they like quantum mechanics, they'll probably say no. It's a stupid, convoluted theory that makes no sense. It does, however, work. And so we stick with it.
Right. Why have the constellations not changed in 50,000 years if we were chasing the sun through space while spinning? And if we were moving, why does the North Star not move and the others go around it?
Okay, so two questions here. I'm going to start with the North Star first. Okay, why does the North Star not move and the other stars go around it? The reason for that is that our axis, the way the Earth is rotating, the axis of rotation, if you think of the Earth as spinning like a top, the center of the top is pointed in the direction of the North Star. So as the Earth rotates, the top of the Earth doesn't rotate. So that North Star, Polaris, is basically in the same spot every night. Okay. Now what's interesting is it wasn't always the North Star. If you go to Egyptian culture, for example, they were fascinated by the star Thuban in the constellation of Draco. The reason they were interested in that star is because at that time, 4,000 years ago, or I guess 3000 BC, basically, Thuban was the North Star. Polaris wasn't. So our axis of the Earth, because it kind of precesses like a top over time, used to have a different North Star. Eventually, in I think 13,000 years, it'll be the star Vega, which is actually brighter. So over time, you would have different North Stars. And if you look at the southern hemisphere, then there is no bright, first or second magnitude star in the southern hemisphere around the southern pole. So all the stars move around. So that's that one. The other one is, why have the constellations not changed in 50,000 years? They actually have. They just haven't changed in a way that you would notice. So we actually see stars drift relative to each other. So there is the motion of stars relative to other stars, and we can actually measure that. And in fact, it was one of the things that we could use to verify the motion of the sun through the galaxy.
In fact, I've got a little animation up here, just briefly showing the object GN05392, which was at one point claimed to be Nibiru on Google Sky. Well, next to it happens to be a high proper motion star, and I'm sorry, I forget the designation of this guy, but he does have a designation that you can look up. And so this consists of two images from the Palomar Sky Survey taken about 30 years apart. I think the first one was taken in the 1950s, the second one in the 1980s. And then my image about 30 years after that. So spanning about 90 years, just about or not 90, sorry, about 60 years, just about a human lifespan almost. You can see the motion of this star over time. And you can see a whole variety of high proper motion stars. This is just one of them, but they do move if you look over a long enough span of time.
This sort of a conclusion now, and what we're sort of going to be asking you. Excuse me. What is your conclusion on Nibiru? Do we have a rogue planet in our system? Is this one big, massive conspiracy theory? Do you have a bunker secretly somewhere that you're going to hide into and leave us all on the surface of the Earth to die? Is this just one big, massive conspiracy theory that we're just trying to fool people? Or is it just, in your expertise, another fake doomsday?
There's no evidence for Nibiru at all. There is no planet coming our way or heading towards Earth or anything else. And one of the standard arguments would be that maybe I'm covering this up, but I can tell you absolutely and certainly that if I were to have evidence for a planet like Nibiru in our solar system, if I were to find a 9th planet and were able to prove that it existed, my university would be overjoyed. They would probably give me a raise and promotion because I would have found the 9th planet in the solar system. We love when theories get overturned, if you can do it. And we give them things that we call Nobel Prizes for overturning or expanding theories that we haven't had. So I would love to find Nibiru to be true, but it's not. And all the evidence that we have points against it. So, I sleep comfortably every night, safe in my bed, knowing that the universe is not out to kill me.
And just a quick thought on the theoretical physicist. I know you don't like to go into person v person, but from the papers you've seen her write and everything, is there any sort of way that we could have mislooked or that there could be represented, or is it just utter nonsense?
No, it's basically nonsense. They're not peer reviewed and they're not accurate. They don't have any level of precision to them. I'm also a bit troubled just by the, I'm going to say I'm a physicist and therefore I'm qualified to do everything. When in my own writing, I don't focus on what my credentials are because it's the evidence and the data that matters, presented clearly and honestly. I think when you have someone outside of the field of astronomy who's claiming, well, because I have a degree in particle physics or whatever, I'm okay to do, astronomy. I'm really leery of that because it should be the evidence that matters. So,
you know, if you were peer reviewing one of our papers, you know, given the 3 choices, accepted, needs revision, or, you know, rejected, what would be your rating on it?
Not even wrong.
Good answer.
I mean, yeah, it doesn't even meet the standard of a scientific paper in these sets. I mean, none of them do. They don't have clear sources. They don't have a history. They use terminology incorrectly in terms of how we would use them, and that's one of the big things, is that when you're in science, you know, definitions matter. So that when I would say, when we're talking about a brown dwarf, I was very clear to specify what is meant by a brown dwarf. Or if we're going to talk about what specific data is, we look at where the data comes from and when it was taken and how it was taken. And that's not done in those papers. So yeah, they wouldn't make even remotely any peer-reviewed journal.
Great, thank you very much.
Mm-hmm.
Dr. Koberlein, you may not know how much this means to us, but I learned a lot myself today, and I hope that the people watching did as well. You guys can go to Dr. Koberlein's blog. It's One Universe at a Time. He has a really, really great blog.
Do you want to sort of give out some links, Mr. Koberlein, of how people can contact you, or, you know, read the information that you're providing?
Sure. So if you go to my website, it's actually briankoberlein.com, so it's myname.com. But the name of the blog is One Universe at a Time. That's where you'll find most of my writing. I do contribute articles to Forbes, so you find me every now and then there. Those are kind of the 2 main things. Every now and then you'll find me at some other sources, but you can certainly post comments on the website, and as long as they're on topic, there's also a contact form there, so I'm pretty easy to find.
Thank you very much. It was, you know, a big privilege to have you, you know, take the time out and do this with us. I think you've eased quite a fair few minds. Okay. I just said the die-hard believers will be the die-hard believers until time proves them wrong.
Yep.
And there's nothing, unfortunately, we can do about, you know, them particular type of people. And I'd like to thank you very much for that, Mr. Koberlein.
Okay, you're very welcome.
Thank you very much, Mr. Koberlein, for coming
Thank you very much.
Thank you.
Yep, you're welcome.
Astronomy Live, is there anything that you sort of, as Mr. Koberlein obviously leaves the hangout, is there anything that you want to continue on with, or?
Nibiru Planet X has finally joined the chat here, but I don't think he has anything relevant or substantive to say. But
he's been given many chances by yourself and Dazza and, you know, Sean to come on, have a healthy debate.
Oh, I know.
And Mr. Koberlein, I won't put you through this gentleman's path, because he'd be one of these. He'd come on the debate. He would listen to what you had to say. You know, he'd be such a gentleman with you. And then 2 minutes later, he'd do a video calling you all the names under the sun. And I mean, he'll attack it. He'd try to get you fired from your work and all sorts. He's a sly ball, I'm afraid to say, and there's no other nicer ways to put it to him.
This is part of the reason why when discussing things in general, you know, I try to avoid personal attacks and just look at the evidence and say, look, you're either right or you're wrong. What your motivations are, you know, is between you and yourself.
Yeah, absolutely.
Well, that's correct. That's how any normal person would debate a subject. But this gentleman is not like that at all. Twiggy, is anything that you'd like to add?
No, I'd just like to add thank you very, very, very much for coming along and speaking to us.
You're welcome.
Thanks, everybody, for joining us. If anybody has any more questions or anything that you know, for another time, you can always ask us at Fact or Fiction. We'll leave links in the description for Dr. Koberlein's website. And I hope you guys enjoyed us tonight. And we definitely had a wonderful time. I did as well.
Thank you very much.
Well, good night, everybody.
Good night. God bless everybody. Take care.
Good night.